So the first trick up our sleeves is about isotopes, isobars and isotones. Okay, I know this can be a bit confusing to remember which one is for what. So here is a trick just for that. Okay, so the first one we have isotopes. Okay, here you can remember that it has a P in it, which means same number of protons, okay, or same Z number. Okay, similarly isobars, you can remember this A, make it capital so that you remember it is same A, okay, same atomic mass number, same A. Okay, and finally we have isotones. It has a N in place of P, which means same number of neutrons. Okay, neutrons will be given by A minus Z, right? Number of neutrons is A minus Z. Okay, so this is a simple way of remembering isotopes, isobars and isotones. Next we have vector triple products. So here we have three vectors A, B and C and a vector product between them. The resultant is of course a vector with some shuffled order of A, B and C. Okay, now on the face of it, it might be difficult to remember, but you can remember one simple thing, that vector triple product is nothing but back-cab rule. Okay, BAC and CAB rule. Okay, so if you see, this is back cab rule. Okay, so A cross B cross C will be back and cab. Of course, there is a dot product over here, dot product over here, and which is multiplied by a vector so as to obtain a vector. Okay, so vector triple product is back cab rule. That is our trick number 2. Next, we will write the 3-bit possibilities or binary numbers from 0 to 7. Okay, so for 2 bits, we know that the possible combinations are 0, 0, 0, 1, 1, 0 and 1, 1, right? That is 0 to 3 in binary. My X was a 10, but in binary. Okay, anyways, to obtain the number of possible combinations, you basically raise 2 to the number of bits. Okay, so in 2-bit combination, it was 2 raised to 2, which is 4. Similarly, for 3 bits, what will be the number of possible combinations? Okay, so it is 2 raised to 3, which is 8. Okay, so 3 bits, so 2 raised to 3, 8 possible combinations, or you'll obtain binary numbers from 0 to 7. Okay, now how do you write this in order? How do you write all the possibilities? That is the question. So my suggestion to you is to write the C column first and write it alternatively with 0 and 1. Okay, so you begin with 0, 1, 0, 1, 0, 1, 0, 1. Right, 8 combinations. So 1, 2, 3, 4, 5, 6, 7, 8. 4 zeros, 4 ones. Okay, alternative. Now repeat each of these combinations twice. Okay, so 0, 0 is the first combination. Repeat it twice. Okay, now 0, 1 we have 0, 1, 0, 1. Okay, now the next combination is 1, 0. So 1, 0, 1, 0. And finally we have the combination 1, 1. And just like that, you have produced all the binary numbers from 0 to 7. You can check it yourself, and that is the trick how you produce 3-bit possibilities from just knowing the 2-bit possibilities. Okay, also you can extend this to 4-bit possibilities and go from 0 to 15. That's up to you. Nuclear quadruple movement. So here it can be either prolate or oblate. Now you don't have to stress your head if the quadruple movement is given and you know the radius, and then you have to manipulate so as to obtain A and C. No need of doing that. Okay, so if you know the quadruple movement and if you know its value is positive, it's basically a prolate, and negative, it will be oblate. Okay, so you don't have to find A and C explicitly to know if it's a prolate or oblate. If you know it's positive, it's prolate. Next is regarding the magnetic field due to an infinite semi-infinite wire and the one produced at the center of the loop. Okay, now these formulae are confusing because either one of them has pi or no pi, right? So these are very similar, but they represent magnetic field due to different bodies, right? So for infinite wire, we have mu 0 I upon 2 pi r. Now to give you a logic for this, why does the pi comes? Suppose we have an infinite wire, we compute this using Amperian loop, right? So we choose Amperian loop of radius r, and we use this BDL is mu 0 times the current I. So DL is 2 pi r, right? That 2 pi r is coming in the denominator. Okay, so B is constant, 2 pi r. So mu 0 I upon 2 pi r. So this is for the infinite wire. Okay, so there is a pi over here, okay, which is coming due to the Amperian loop. Now for semi-infinite wire, you just, semi is half, right? So just half it. So 4 pi r. Of course, that is not the logic, but that is a way to remember. And for loop, there is no pi. Okay, this you obtain explicitly solving your Biot-Savart's law for magnetic field at an axial point. Then you put, then find at the center, right? Putting x equal to 0. But anyways, there is no pi for loop. Okay, you can remember for wire there is a pi because we use the Amperian loop. Okay, and for a loop there is no pi. Okay, so it's basically mu 0 I upon 2r, where r is the radius. Here r is the perpendicular distance from the wire. Okay. Next is to find the gradient of 1 by r, where r is the magnitude of the position vector. Now there is a whole derivation sort of a thing for this at the undergraduate level, but we can do it in simpler ways. Okay, and it will also brush up a concept. So we can use actually the definition of electric field as the negative gradient of potential. Right, we know that electric field, simply you can write it as kq by r square, and of course it's a vector, so we'll use r cap along the r cap direction, and here we'll have negative gradient of kq by r, right? That is how the potential is defined. It's a scalar, so no direction, hence. So you can cancel this kq, and what you'll get is this gradient of 1 by r. You can see that gradient of 1 by r is nothing but minus 1 upon r square r cap, or you can see that basically it's a derivative of 1 by r, right? Minus 1 by r square, and in that particular direction r cap. Okay, so this was there in one of Richard Feynman's book. Okay, I'll mention all the sources of all these tricks in the description box. Of course, some of them are my own khayali pulao, but most of them are from other teachers and some books. Okay, so I'll mention that in description. Okay, for 7 we have brevis lattices, although there are 14, but 7 crystal systems, so that works out coincidentally. The phrase to remember over here is cute R mother. Okay, so from this phrase you can create all the crystal systems. So Cu cubic, Te tetragonal, O orthorhombic, R rhombohedral, Mo monoclinic, T triclinic, He hexagonal. Okay, so now you have created the crystal systems, but what about the lattice parameters? Okay, A, B, C, and alpha, beta, gamma. Since that there is also a way for it. Okay, so you can remember that the first 3 are orthogonal, meaning all the angles will be 90 degree. Okay, only the sides should be cut down, the number of equal sides. Okay, so for cubic all the sides are equal, tetragonal one side unequal, orthorhombic no sides equal. Okay, all the sides unequal. Okay, so you can do this. Okay, orthogonal and cut down one equal side at one time. Okay, now rhombohedral is the first one that breaks this orthogonality conditions. All the angles will not be equal to 90, so one angle will not be equal to 90, but it maintains the cubic thing. Okay, so A equal to B equal to C, but only it breaks this condition. Okay, now monoclinic, you'll see that you can note that all the things that all the crystal systems that end with IC will have all the sides unequal. Okay, IC all sides unequal, unequal, unequal. Okay, so that is a pattern to note. So, and also this shows tricli and monocli, right? So this is the number of mono is 1, right? Mono one angle is not equal to 90. Okay, and that is beta for monoclinic. Okay, and triclinic you have all the 3 angles, 3 tri is 3, right? So 3 angles not equal to 90 degree. Okay, so it's simple IC all sides unequal, and triclinic 3 angles not equal to 90, monoclinic one angle not equal to 90 degree, and that happens to be beta. It's a special case. So beta you have to remember over here. Okay, it's other two are equal, alpha and gamma. Okay, equal to 90. Finally, coming to hexagonal, it's again simple. You can imagine a hexagonal thing. Okay, I'll use a different pen. Hexagonal is like this, right? Parallelogram, the primitive unit cell. Okay, I'm not speaking of hexagon. PUC is like this, right? So hexagonal. So if you see this angle, or I should have drawn it like this. So this angle is 120 degrees. So gamma is 120, right? All the other angles are 90 degree. Of course, the angle made with C, with A and C and B and C, those are C is like this, right? So those are 90. Okay, so those are 90. Only the angle in the plane, which is gamma, is 120 degrees. Okay, and also these two sides are equal, and the C side will not be equal. Okay, so you just have to picture a parallelogram for that. Okay. So those are our crystal system or our brevis lattices. Right, we have resistances in parallel. Now this is something that I have been using on the channel for a while, so I thought of showing it to you, and I've spoken about it in a number of videos. So if you have 2R and R in parallel, basically the equivalent resistance will be the bigger one, the double of the R by 3. Okay, so this is being worked out over here. It's basically a simple math behind it. Okay, and it becomes significant because a lot of questions you'll see such type of circuits, right, wherein the resistances in the branches one is double of the other. So basically you take the bigger one, the double one, and divide it by 3. So, example, 6 and 3 in parallel will give you 2. Okay, and for this to if you want to remember the formula for R effective, one of our teachers used to say it is MA, right, multiplication upon addition. Okay, so multiplication upon addition. Okay, so that's a simple trick I wanted to share because I use it in a number of videos. So let's come to beta minus and beta plus decays. So some of you might already have tricks regarding this, right? If you say beta minus, it does z plus 1, and beta plus is z minus 1. Beta minus is electron, and hence anti-neutrino. And here it's positron and neutrino. Okay, but let's go one step behind and let's see what is actually happening. Okay, so that you'll have a better understanding. And the best way to remember is to have an understanding of something, right? So beta minus, we have electron, so electron is being released, and hence we will have anti-neutrino. Okay, so just to balance the mass, energy, or end momentum. Okay, so beta minus, we have electron and anti-neutrino. Okay, so something has to convert into electron. Okay, of course a proton cannot convert into an electron, so a neutron will convert into proton and electron, right? Neutron can break into proton and electron. This seems feasible. Okay, and if you see what happens over here, neutron changes into proton. Okay, so nucleon and still a nucleon, right? So A will not change. A will not change because this is also contributing to A, and this is also contributing to A. Okay, so A will not change. But if you see neutron, it is not contributing to Z. Okay, but proton is contributing to Z, the atomic number, right? It's the number of protons. So Z. So here, in going from here to here, you have increased a proton. Okay, you have changed a neutron to proton. So hence Z plus 1. Okay, because this is contributing to Z. Okay, similarly here what will happen, we'll have a proton going to neutron. Okay, and of course beta, so we should have started it like this. Beta plus is positron, so positron and neutrino, and then what will break into this plus charge, we want plus charge, so we have a proton, right? Proton goes to neutron and neutrino. So here if you see proton, neutron, nucleon, so A again does not change, but this is contributing to Z, but we have converted it into something which is not contributing to Z, so Z minus 1. Okay, so that is the logic behind this. Of course you might have your own tricks regarding this, but it's always better to understand, right? And fun fact, this reaction is actually not possible in free space. Okay, but we do see beta plus decays in nature, right? So do explain me about that in the comment section. Why is this reaction not possible, but we do see beta plus decays? So 10, we have De Morgan laws, or as I would like to call it today, break the line, change the sign. So if you have A into B the whole complement, it's basically A complement plus B complement. Okay, so you have to change the sign and you have to break the line. Break the line, change the sign. Okay, A plus B the whole complement, break the line between A and B and change this sign. Okay, so break the line, change the sign, and you can in fact do all of this within the set theory. Okay, you can replace this dot with intersection and plus with union, and you'll have the same laws, right? In math in set theory. Okay, so you can actually in fact do your +2 digital electronics with the help of set theory and not at all learning your Boolean laws. Okay, so break the line and change the sign. So Lagrangian and equation of motion. So Lagrangian, as we know, is a function of coordinate. It's time derivative and may not be explicitly dependent on time. We can have two equations, dou L by dou Qi. So partial derivative with respect to your coordinate and partial derivative with respect to coordinates time derivative. Okay, so here the pattern is simple. It will always give you P, and for Lagrangian it's always positive. Okay, you can do it for Hamiltonian, it will be negative in certain case. Okay, but for Lagrangian you'll get P. Okay, P or Pi dot depending on the case, and it will be always positive. Okay, P for Qi, it's Pi dot. Okay, you can note the pattern over here. Qi dot will give you Pi. Okay, so it's dot when there is no dot over here. If it's a dot over here, there is no dot over here. Okay, so alternative. Okay, so that is those are the two relations, and we'll have to write the equation of motion now. So the thing to decide is whether this term will go over here or this term will go over here. Okay, so some of you might know it by heart, but the trick is to obtain Newton's second law, which is force is mass into acceleration, or more better, force is a rate of change of momentum using this. Okay, using this now. So if you see, if we put this over here, what is this? Dou L by dou Qi dot. So rate of change of momentum, right? Rate of change of pi. So we can put this over here, dou L by dou Qi dot, right? So this is rate of change of momentum, which is nothing but force, right? This is force, and this minus I can take it on the other side. So I'm writing equal to, and what is this? The other term that is remaining is dou L by dou Qi, right? So this is nothing but pi dot. So force is nothing but, so basically you obtain pi dot and pi dot on both the sides. That is how you obtain equation of motion, right? So this is force, rate of change of momentum, and this is pi dot, which is the same thing, right? So yeah, that is how you can remember the equation of motion and the Lagrangian. Okay, you can proceed for Hamiltonian as well. A sign will change somewhere. Okay, so that you'll have to take into consideration. 13, moment of inertia. So here we have different bodies like solid and hollow spheres with their forms of moment of inertia as 2 by 5 and 2 by 3. So there might be a confusion over here so as to which one is which one is solid, which one is for solid, and which one is for hollow. Okay, similarly we have a one-dimensional rod and its forms along two different axes. So there might be a confusion in this. So let us destroy this confusion using a simple idea, okay, that moment of inertia is nothing but inertia in rotational motion. Okay, and what does inertia do? Inertia preserves motion, right? So if a object is already moving in rotational motion, if it has higher moment of inertia, it's difficult to bring it to rest, right? Or vice versa, if you want to bring the object to rotational motion, okay, it's difficult if its moment of inertia is higher. Okay, so higher moment of inertia means it's difficult to rotate basically that object. Okay, so if we have a solid sphere and hollow sphere of the same mass, which one is difficult to rotate? Now it's quite intuitive if you think about it. If they have the same mass, of course, if you see the solid sphere has distributed mass, right? So an axis passing through, of course, though these two axes are passing through center of mass, so x is passing through center of mass, the mass is distributed, right? So it's easier to rotate, right? Whereas for hollow sphere, inside it is hollow, all the mass, okay, equal to this mass is distributed only on the surface, right? So it's difficult to rotate. All the mass is away from the axis. Okay, so this one should have higher moment of inertia, right? Because it's difficult to rotate basically. So this one will have higher moment of inertia, which is 2/3, right? 2/3 is bigger than 2/5. So 2/3 mr square is for this one, and 2/5 is for this one. Now again, the question arises over here: which one is difficult to rotate? Okay, if it's about this axis, is it difficult to rotate, or is it about this axis that is difficult to rotate? Okay, if you see about this axis, about the axis passing through the middle, it's quite simple, right? Because the mass is distributed, and along this axis, the mass is very far away from the axis, right? So it's difficult to rotate about this axis for the same mass. Okay, so this one it's difficult to rotate having large moment of inertia. Which one is that? Okay, larger moment of inertia for this one. Okay, so it is ml square by 3 over here, ml square by 3, and this is easier to rotate, meaning this is ml square by 2a, right? Smaller, very. So that's it. 14, density of crystal. Okay, so density basically has the definition of mass by volume. So volume for a crystal can be a cube, right, in terms of the lattice parameter. So mass by a cube, and then we can have the two numbers, molar mass. So we can have the Avogadro number Na, so m by Na, and there are n effective number of atoms in the crystal cell. So you have to multiply it by two numbers. Okay, so that is how I remember this formula. So mass by volume, and you have to multiply by two numbers, molar mass divided by Na, and n effective times the mass, right? Because there are n effective number of atoms in the crystal cell, or the volume is divided among n effective. So either it's a cube by n effective. Anyways, you can remember it that way also. Okay, and fun fact, 1 upon Na is equal to 1 AMU. Okay, so this is the reason why if you are given the mass in AMU, you don't need to use this Na. Okay, if it's in AMU, you can just use this formula, okay, without the Na, and you can, and if you are unsure about the values of this, any one of them, you can derive it using the other. Okay, so 1 upon Na, this is about 6 into 10 to the power 23, right? So this will be around something 10 to the power minus 24. Of course, you will obtain it in grams, and it will be 1.67, right? So these are reciprocals of one another. You can use one to compute the other. Interesting. 15, partial differential equation for heat and wave. Okay, so for wave equation, it's simple. You have the second derivative in position. You have to relate it with second derivative in time. Okay, or else I'll write it in this form. Okay, so here we'll have like this. Okay, now it was a hard time for me to remember where does this v square come. Is it on this side? Is it this side and denominator? Is it this side and denominator, or this side on top? Okay, it was quite difficult for me until I noted that this satisfies the dimensions, right? This is distance, this is velocity, time. So distance is velocity into time, right? So you can remember it. So basically wave equation is second derivative in x is related to second derivative in time. Okay, and you can put this v accordingly, v square accordingly, by checking the dimensions that the denominator gives you. Distance is equal to velocity into time. Okay, so that is how I remember it. And for heat equation, again left hand side is same, you can compare. It's second derivative in position. Okay, write it as h, and it is, we have diffusivity over here, okay, in place of v square. So first you write this and then you can get this. Okay, only difference is it's first derivative in time, second derivative in space, first derivative in time. For wave, it's second derivative and second derivative. Okay, second derivative space and second derivative in time. Okay, here is the only difference for heat equation. 16 are the cyclotron results. Okay, this is one of the simplest trick in your book, because basically in cyclotron what happens is that the centripetal force is provided by the Lorentz force, right? And we have perpendicular magnetic field to the motion, so it's basically the sin theta is dropped. Okay, so mv square by r is qvb. Okay, you just need this one thing to derive all this formulae. Okay, so r, from here you can see that it is mv by qb, one v will cancel. T you can find by 2 pi r by v, okay, because it's revolving in a circle. So 2 pi r by v, so r, if you substitute, you will get 2 pi m by qb. Now I have practiced it a lot, so I remember it myself. And here for this you have to just divide it by 2 pi and take the reciprocal, so qb by m. Okay, so these are your cyclotron formula for angular frequency or time or radius. Okay, you can derive it from this one simple relation. 17 is about thermal conductivity. Okay, it's a fun result. You can compare it with your Ohm's law. Basically, you have thermal conductivity, the equation for heat current, which is rate of heat by time, which is the heat current, IH basically. You can compare this current with respect to your actual current, okay, conventional current by Ohm's law, which is delta V by R. Okay, so similarly, here we have Ka delta T by L, right? So here we can bring this Ka down, so you can compare this and this equation. So basically you will obtain that the heat current is proportional to your temperature difference, and this is the resistance over here, L by Ka. Okay, so similarly you can have this conductors in series and parallel, just like your resistance, and you can find the heat current. Okay, also you can have them in series and you can find the junction temperature. So it is an interesting concept which comes out by comparing your heat, okay, the rate of heat flow to your Ohm's law. Okay, so yeah, first nearest neighbors. Okay, so here the simple trick is that if you find the first nearest neighbor along the axis, the number will be 6 first nearest neighbors, and if you find it in a plane, it will be 12. Okay, so I can provide you the logic over here. You can see it, actually imagine it. So here if we have a crystal cell and we have the first nearest neighbor along the axis. Okay, so if this is the first nearest neighbor, it's along the axis, right? So what will be the number of first nearest neighbors? 1, 2, 3, 4, 5 and 6, right? So in simple cubic, this is the case of simple cubic, you can see that it is along a axis and hence the number will be 6. So if we come to the case where if you find the first nearest neighbor in a plane, for example for face centered cubic, okay, you'll have the first nearest neighbor in a plane, right, along the face, okay, in that face, so here and here, okay, so like this, somewhat like this. So in this plane, so here you'll have what will be the first nearest neighbors? 1, 2, 3, 4 in a plane. Then you'll have a plane like this, so 1, 2, 3, 4, it's hard to imagine, but yeah, you can give it a shot. And one more plane like this. Okay, so 1, 2, 3 and 4. Okay, so 4 in each planes, there will be 3 planes. So the first nearest neighbors in a plane is 12. Okay, so basically the trick is, if you find the first nearest neighbor along the axis, it's 6. If you find it along the plane, it is 12. Okay, it works for FCC and SC. Okay, and you can also proceed with this logic to find second nearest neighbor. Okay, so if you see, for simple cubic, the second nearest neighbor is in the plane now, right? This is along the diagonal, right, in the face plane. Okay, so this plane. So here, for uh, simple cubic, since it is in the plane, it will be 12, I told you. And for FCC, you can see that the second nearest neighbor will be now along the axis, so it will be 6. Okay, so you can proceed with this logic. It will be slightly trickier for body centered. Okay, this will fail, because first of all, there is an atom in the body center, and it's not actually along the axis or plane, right, the first nearest neighbor. Okay, so that will fail over there. Okay, so the short trick here is 6 along axis, 12 along plane. 19 is symmetric and asymmetric potential well. Okay, and let me promise you this over here, that you don't need to remember one single thing over here. Okay, so here, if we have symmetric and asymmetric potential well, symmetric of course is minus L by 2 to L by 2, right? Symmetric about the 0, and here 0 to L. It's basically not symmetric, right? So you can note the ground state wave function will be something like this, right? So if you see, let us see for the asymmetric case, you can see that it is going to 0 at 0 and L, okay, and it's maximum somewhere in between. So it is kind of like a sine function, 0 at 0, 0 at L. Okay, so L, that we can adjust. Okay, 0 at 0, it is sine, right, basically. So we'll have the sine function and n pi x by L. Now this is very interesting, because this n pi x by L is basically k. Okay, what we are doing with this k is that basically we are adjusting the old period. Basically, if you see, if you drop this n is basically for the number, right, the number of state. Okay, ground state n1. Then you go to the higher excited state by changing the value of n. Okay, so if you see, it is basically pi by L. Okay, so for the ground state, you can see pi by L, right? So pi is the old period, okay, and L is the new period. So basically, you are fixing the old period, right? Sine function goes like this, right? Old period is something like this, right? So old period pi, whatever was there in pi, you are fixing it in L. Okay, whatever was there in the pi interval, you are fixing it in L. That is the significance of k. Okay, and that has to happen given the boundary conditions, right? So similarly, for this symmetric potential well, you can see that this is of course goes to infinity. Symmetric potential well, so you can see that at 0 it is becoming maximum. So it is like a cos function. Cos 0 is maximum, right? So it is again same form, and you are fixing pi between the length L, right, minus L by 2 to L by 2, which is again L, right? So you fixing the period pi, whatever is happening in pi, you are fixing it in L. Okay, and again you can do it for excited state as well. So this is for excited state, n becomes 2, right? So 2 pi by k becomes 2 pi by L. So whatever was happening in 2 pi, you fix it in L, right, for excited state. So that is the logic over here. So you can remember a sin kx and a cos kx. This is symmetric, this is asymmetric. Okay, no need to remember, you can interpret it via logic, right? And this is one of the concept that is used in your Fourier series as well. Okay, but Fourier series can be a whole video for whole different video, right? It has so many things, interesting things, but anyways, we'll keep it out of discussion over here. And as far as energy is concerned, again, you don't have to remember anything except that it is p square by 2m and p is h cross k. Okay, those are trivial things, you will know them. So once you reach here, you can just substitute this k, right, a sin kx or a cos kx, this value, and you will get the energy for one dimensional potential well, symmetric or asymmetric, that doesn't really matter, right? Same for both. So yeah, that is how you obtain all these relations for symmetric and asymmetric potential well. 21 is Miller indices. Now Miller indices, there is a systematic approach to obtain it, but let's cut out the crap and do it via a shortcut. Okay, the shortcut is you take ABC and take its ratio or divide it by PQR. Okay, what is ABC, what is PQR? So ABC is basically your lattice parameters, their values, and PQR are your coordinates, okay, or the intercept. Okay, P is the basically you'll have a axis, sorry, basically you'll have a plane, right? that will make intercept on A, B and C axis. Okay, so these are the intercept. T is the intercept on A axis, Q is on the B axis and R is on the C axis or XYZ axis. Okay, so ABC are your lattice parameters, PQ are your intercepts. Okay, and now that I have told you this, you might also confuse that whether ABC is on top or PQR is on top. Okay, that type of confusion can also arise. One thing to remember is that Miller indices are calculated, are obtained in a reciprocal space, right? So of course the coordinates that are over there, which is PQR, the intercept, will be in the reciprocal, right? It's in the reciprocal space, so PQR will come in the denominator. So you take A by B, B by Q and C by R and take their ratio. That will give you the Miller indices. Of course Miller indices can, this ratio can turn out to be negative in some cases, so you'll have to use the bar, and needless to say that if there is a fraction, you have to multiply by the LCM, right? Though that procedure follows logically. Okay, so this is how you obtain Miller indices. And let me know what will you do if the plane whose Miller indices you want to find passes through the origin. So I mean P is 0, Q is 0 and R is 0. What will you do in that case? So that is something to ponder about for you, and tell me in the comment section below. So 22, we have partial fractions. Now this is useful in, I think, Laplace transform, and you can also use it for simple integration, right? You cannot integrate this, but if you have something of this form, you can integrate, right? So this is useful for those purposes, and we do use it in physics, like Laplace transform I told you. So here basically you have something in the product in the denominator, and you can split it like this. Okay, it's a linear case. If you have x square and all, the expansion is different. Okay, now here the objective is to find A, B and C. Now this can be done by taking LCM, and this 2 will come with A, this x minus 1 will go, and this 2 will come with B and so on. Okay, and then you can cancel the denominators on both the sides. Okay, y you can write over here, and denominator you can cancel. You can put certain values and find equations, solve them and obtain A, B and C. Okay, but that is the long way of doing it. Let's cut the crap and let's see how to do it in a short way. Okay, so if you want to find A, substitute what makes this term 0. Okay, so substitute x is equal to minus 4, right? This is for A, because if you see in A we won't have this, right? I'm not going to provide you the logic because it might confuse you. Okay, so if you substitute x is equal to minus 4, we'll obtain the value of A. So you have to substitute x is equal to minus 4 in this equation. Okay, because in A this and that will get cancelled, if you can imagine it. Okay, so in this equation you can substitute x is equal to minus 4. Okay, this term will go to 0, right? So I'm avoiding that. So x is equal to minus 4, this will be 16. This will be 6 into minus 4 plus, okay, so that will be 6 4s are minus 24. Okay, and here we have 9, right? And then we'll have here what we'll have, this is minus 5 and this is minus 6, right? So if you see, this is 15, 15 minus 25, minus 24 1, and 5 6 are 30, right? Similarly you can obtain B. For B what you'll have to do, you'll have to put x is equal to 1, because that makes this term 0, and avoid this term, because for B that and that will get cancelled, right? So just substitute x is equal to 1 in this equation, and similarly for C, just substitute x is equal to 2 in this equation. Okay, and that is how you obtain A, B, C, and then you can integrate or do whatever you want to do with this simple form of y. Okay, so that is how you do partial fraction. Next is volume of reciprocal lattice. Now this can be a bit tiresome process, that we have to go from the lattice vector of one lattice to its reciprocal lattice vectors, and then find the determinant of that or the scalar triple product of that reciprocal lattice vectors to get the volume of the reciprocal lattice. Okay, instead of that we can use this simple formula that volume of the reciprocal lattice will be 2 pi cube by volume of the direct lattice. Okay, now let's apply it for a case and see. So for FCC we know that the reciprocal lattice is the BCC. Okay, so the volume of our reciprocal lattice, which is BCC, will be 2 pi cube volume of FCC, right? I'll write directly, this is BCC is volume of FCC. Okay, so we are going from FCC direct lattice to BCC, which is, it's a reciprocal lattice, And what is the volume of FCC? Volume of FCC is basically, okay, again you can use its reciprocal vectors, okay, sorry, its lattice vectors, because it's a direct lattice, and you'll obtain a cube by 4, right? Or you can use the logic basically a cube and you have n effective, right? This is the volume of direct lattice. So this is one more thing to remember, a cube by n effective. Okay, for FCC it will be 4. For BCC, if you were going from BCC to FCC, this would have been a cube by 2, right? So for FCC, now volume of FCC will be a cube, but it is divided among 4 atoms, right? A cube, it is divided among 4 atoms. So what is the value of this volume of BCC? Volume of this BCC, which is the reciprocal lattice of this, is 4 times 2 pi by a the whole cube, right? This is the volume of primitive BCC cell for this FCC. You can also obtain for conventional cell, it will be BCC, right? Conventional BCC, if you want, you have to multiply it by 2, okay? So yeah, this is a shorthand way of finding the volume of the reciprocal lattice when you're given the direct lattice. And for direct lattice, this is the formula, okay? A cube divided by the among how many atoms is a cube shared. So 24, we have the Schrodinger time dependent equation. Now this might seem daunting, but if you do it the right way, it's easy to remember. Okay, so here it's simply H psi is E psi. Okay, H we have kinetic T plus V, right, Hamiltonian, and it's in the operator form. So this is T, P square by 2m. Of course, it's in the operator form, and the potential psi and E psi. Okay, energy operator, and you can remember these two operators, okay, very important, IH cross dou by dou x, and energy operator is IH cross dou by dou t, right? So these are just substituted over here, p square, so square this, minus goes, I square, minus sign again comes, h square by this 2m, right, and then double derivative, right, p square, then v psi, then energy operator IH cross dou psi by dou t. Okay, so that's basically E, H psi is E psi, H being T plus V, right, kinetic energy plus potential energy, and you just have to know the operator forms to obtain the Schrodinger equation. It seems daunting if you want to learn it from here, but if you go stepwise, it's quite H is equal to T plus V. Bonus trick, since you made this far into the video, okay, so once I came to know about this trick, I stopped dividing by 5, okay. This is the thing that I do, okay, unless I have to, I don't divide by 5, but in case if you see it's a multiple of 5, you can directly proceed that 5 2s are and 5 1s are, right, this is simple. But what about the cases when it is not a multiple of 5, okay, I say don't divide by 5, multiply by 2, okay. What is 72 2s are? It's 140 and 4, which is 144, and shift the decimal, okay, once. This works basically because 5 2s is 10, right, I'll leave it up to you. And 54 by 5, just double it, what is that, 108, right, 108, so 10.8 is the answer over here. You can do it for any number, okay. I say don't divide by 5, multiply by 2. 26 is eigenvalues for 2 cross 2 matrix. So if you have a 2 cross 2 matrix, you don't need to do 1 a minus lambda I and then equate it to 0, find the characteristic equation, and then solve the quadratic to find lambda, right. The simple formula that you can use over here, this is only valid for 2 cross 2, is lambda is m plus or minus under root m square minus determinant of that particular matrix, okay. So you can try it out with the matrices that you might have done in your undergraduate levels, okay. Find the eigenvalues for 2 cross 2 matrix. Here m is basically trace divided by 2. Trace is basically the sum of the diagonal elements, okay. So a11 plus a22, okay, basically the diagonal elements, you add them, that is the trace, divided by 2, that is your m. Also find the determinant and just solve this, okay. It's quite faster than the solving the quadratic equation. 27 is a flow for telling whether it's normal Zeeman, anomalous Zeeman, or Paschen-Beck effect, okay. Further, you can also extend your knowledge using the selection rules that I've provided to calculate the number of lines, okay, number of spectral lines that you'll obtain in each case, okay. So if the magnetic field is strong, okay, it's no other debate, it's no debate over here, it's Paschen-Beck effect, and you'll have the energy levels modified by ml plus 2ms, okay. So you have to find possible ml and ms for each level and use ml plus 2ms in to find the number of lines that energy levels that it will split in, and then use the selection rules to find the number of spectral lengths. Okay, then if the magnetic field is weak, okay, in that case it can be normal or anomalous. Okay, normal if the transition is from singlet level to singlet level, like 1d to 1p, okay, or 1p to 1s. Okay, so if it's 1 1, I mean when s is 0, right, 2s plus 1 is 1, right, that is the multiplicity I was speaking of, like 1p to 1s. Okay, so 1 1, so multiplicity is 1, sorry, so s is 0, right, so s is 0, singlet to singlet transition, then it is normal Zeeman effect, you don't have to do anything, three lines will be obtained. Okay, so that's your answer. Okay, and weak, if it's weak, okay, we have a debate, right, it can do anomalous or normal Zeeman effect in the case of weak magnetic field. So if it's not in any other case, when it is not singlet to singlet, okay, it can be any other case, for instance 3d to p, p1p, whatever, uh, so those transitions can be anomalous Zeeman effect, will be anomalous Zeeman effect in case of weak field. Okay, so I hope the flow is clearly understood, and in case of anomalous Zeeman effect, the selection rules are this. Okay, so you just have to find possible mj's and watch for mj equal to 0 and mj equal to plus minus 1 transitions between the levels. Okay, and here we have ml and ms for the selection rule because it includes ml and ms, of course. So 28, we can have cos theta and cos hyperbolic theta, and then there is a confusion that where is this I and where is that I not there. Okay, so the simple thing to remember is your identity, Euler's identity, right? So from this you can obtain cos theta, you can add e raised to power I theta and minus I theta, and that will give you, so you can see basically I theta will come for thetas, right? Simple cos thetas. Okay, so according to your Euler's identity. Okay, so this I will be there for simple thetas. Okay, and of course for sine there is a I over here, so you'll have 2I in the denominator. Okay, and for hyperbolic there is no I as such. Okay, there is no. For sine similarly you'll have no I, just a minus sign. Okay, just a minus sign. Okay, that will give you sine hyperbolic. Also you can note that if you replace this theta with I theta, okay, it will give you cos hyperbolic theta, right? Because this will become I square, it will be minus theta, and this will be I square minus I square, so that is I e raised to theta, right? So you can do this substitution to obtain hyperbolic theta. Okay, so you can go from cos, so imaginary angle in cos theta will give you hyperbolic theta. That is the idea over here. Of course this will change for sine, this is not in general, sine of I theta will be something else. Okay, so it will be related, since there is a I over here, it will complicate things up. Okay, it will be slightly different. So that is how you remember your hyperbolic and normal trigonometric functions. Coming to nuclear orbitals feeling, okay, it's quite peculiar from the atomic orbitals, right? It's not at all what you see in the atomic case. So here the orbitals are just seem pretty random, right? And higher J values occupy the lower energy levels. That is one point to remember. And the order is quite random, right? So you'll have to remember this pyramid. Okay, of course you can make your own phrases in these scenarios. Okay, so here it is SPP, DSD, FPFP, GG, DDS, HHF, something. Okay, so that is how you can remember this pyramid, and from there onwards you can proceed. Okay, so of course with this video I'm not assuming that you learn all of these 30 tricks within a day, but I want you to learn the approach. Okay, this trick each had something fascinating about it, right? Some logic or something that can be related, some jugaad that can be done, and the things could be made easier. Okay, so I want you all to adopt the approach, not the actual trick. Okay, so if you do adopt the trick or not, it's not of a concern to me, but yeah, the approach is very much what matters. Okay, anyways, let's come to this trick. Here we'll have s half, half, half. Wherever there is s, it is only half. Okay, for p we can have 3 by 2. You can just go adding 1 in this direction. 3 by 2, 5 by 2, 7 by 2, 9 by 2, 11 by 2. So I'm adding 1 1 1 in this direction. Now p will be 3 by 2 and half, right? So those are the 2j values for your p orbitals, 3 by 2 and half. So similarly for d it is 5 by 2 and 3 by 2. one less. Okay, so from here it will start 5 by 2 and 3 by 2. Okay, then F is 7 by 2. P, again there is no P over here, so it will start with 3 by 2. Okay, and this P will be 1 by 2. Okay, 3 by 2, 1 by 2. So higher J will come first, then lower J. Okay, so 7 by 2 minus 1 is 5 by 2. So in this direction it is minus 1. Okay, so you start with 3 by 2 minus 1. Again you start by 5 by 2 minus 1. S is half, of course. This F and this F you have to go minus 1. So if you're going this way, it's minus 1. 3 by 2. So again we assign this 3 by 2 directly, and this is half, because you basically assign the highest value and then do minus half or minus 1. So 9 by 2, again G appears, so 7 by 2 minus 1. Now D, what is the highest value? 5 by 2, and then you do minus 1, so 3 by 2. Okay, so that is the trend. Okay, and you can also remember the feeling. Okay, here you can feel 20 nucleons. Okay, so this will be plus 8, right? So basically the nucleon number is over here, right? 3 plus 1, the numerator plus 1, that amount of nucleons a level can hold. So this is 28. What is else? I think this is 50 and this is 82. Let me check that. 50 and 82. Yes, 50 and 82. Okay. So this is how you can feel the nucleons and find the parity. Use your Nordian rule or whatever and find the parity. Okay, so it's a bit untrivial to memorize this order, right? SPP, DSD, FPFP, GGDDS, HH. Okay, that we don't know. So yeah, remembering that order, you can compute the nuclear parity. So 30 is about Maxwell's thermodynamic equations. So there are 16 of these equations, and all this you can memorize with the help of this phrase or this diagram. Okay, the phrase is good physicists have studied under very fine teachers. Okay, if you're here watching this video, listening this from me, I should be proud. Okay, anyways, so the phrase is good physicists have studied under very fine teachers. Okay, so this is the diagram. Okay, the letters have their usual meaning. Gibbs energy, Helmholtz energy, internal energy, free energy. Okay, temperature, pressure, entropy, volume. Okay, now these are something I expect you to remember. Okay, these are simple relations. Okay, the first one is itself conservation of energy, or thermodynamics first law, right? Heat provided will increase the internal energy, and some amount will go to do the work. Okay, so Q is equal to U plus W. Okay, also H is equal to U plus PV, you learn this, and F is equal to U minus TS, G is equal to F plus PV. Okay, I expect you to remember this. Okay, rest all we can derive using this. Okay, it's very simple. Now if we differentiate this, okay, what will we get? Differentiating the energies. Here the energies are over here. Okay, now each of the energies will depend on the adjacent terms. Okay, so for example, let's begin with internal energy. Okay, internal energy is over here. So V and S. So it is a function of V and S. So you'll have dV and ds. Okay, it's a function of dV and ds, right? And I want you to remember that whenever you see dV or dt, partial or complete derivative, it will be negative. Okay, like in this case we have dV, right? So it's negative. Everywhere if you see dV, dt, dV, dt, anywhere will be negative. Okay, for the course of this trick. Okay, so here dV is negative, and basically you have to find its complement, right? PdV. So basically this is energy. What will make energy? TdS or PdV, right? Temperature and volume are conjugates, right? These two are conjugates. Pressure and volume, if you multiply, you get energy. Temperature and entropy, if you multiply, you get energy. Okay, so these are conjugates. So if you have dV, so currently you have this, right? You know that du is a function of dV and ds, so you had this, and then what do you multiply with volume? Pressure, right? What do you multiply with entropy? Temperature, to get energy. Okay, they are opposite, if you can see. Okay, also we can do for one more. Suppose dg. Okay, Gibbs energy we have between temperature and pressure. So dt and dp. I told you dt, wherever you see it, negative. dt and dv, negative, right? So what do you multiply with T? You multiply S. What do you multiply with pressure? Volume, right? They are conjugates. Okay, if you multiply them, you'll get energy, and this is energy on the right hand side. You want energy, so you multiply them. Okay, You can do for df and dh, okay, and prove me correct, okay, or wrong. Then let's come to this. This will touch upon finally, okay, because these are the terms, okay, temperature, pressure, parameters, volume, and entropy. Okay, you can actually see it from here, but let's keep this for the time being. Let's come to this. Okay, how do we? These are the four Maxwell equations. You might be sometimes asked to derive them, right, in your course. But how do we get this from this graph, okay, or this plot, whatever we have over here? So it's simple. You just have to go dp by suppose this one we want, right? So it's dp by ds and dt by dv. Now I told you whenever there is dv in the denominator, here in this case it will be differentiate with respect to v. Okay, so here also it is differentiated, right? So here when it is differentiated with respect to v or t, okay, in the denominator you have dv or dt, it should be negative. Okay, so let's come to this one. This is dp by ds, right, and dt by dv. Okay, those two will be equal, this by this and this by this. Okay, you can do it for like this also. Now we can do that. Where is that? dp by dt, okay, and ds by dv, both are negative, right? Dt with respect to dt is negative, with respect to dv is negative, so that negative sign cancels. You can come to this one. We have dv by ds, okay, and dt by dp. Nothing, dv by dt is not in the denominator, okay, it's not differentiated with respect to dt or dp, right? We have ds and dp, so those in the denominator does not make difference. Okay, if only if dv or dt comes in the denominator, it is negative. Okay, dv, dt, dv, okay, here. So you can derive the remaining one also, dv by dt like this, ds by dp, right? Let's come to this one. This one you can actually see it from here. Now if you want temperature, you have it here and you have it here, right? So either it's du by ds, right, du by ds, or dh, dh by ds. Okay, yes, and the other variable is constant. Like in this case, volume is constant, other variable pressure is constant, right? Other variable pressure is constant. Let's do it for one more. Volume. If we want volume, where is volume? Here and here, right? Let's do it for entropy. Okay, it doesn't really matter, but this is quite important, so I'm focusing on that. So entropy, if you have it over here, so it is dg by dt. Wait, where is that? Dg by dt, right? Dt, and the other variable is constant. Dg by dt. Other variable p should be constant over here. I may have made a mistake. Okay, and this is df by dt. Df by dt, other variable, volume is constant. Okay, fine. So that is that. Also you can see this. If you want temperature, you can get it from here. du by ds is temperature. Okay, and similarly dh by ds is temperature. If you want entropy, suppose entropy, you can get it from here. Df by dt is entropy, dg by dt is entropy at constant volume, at constant pressure. Okay, so yeah, that is how you obtain all these 16 relations, or rather 12 relations, those I asked you to remember, from this Maxwell's diagram. Okay, so those were all the 30 tricks that I wanted to share with you in this video. I hope you really enjoyed it. I hope you could pick on some of this trick, and this will change the way you look at physics. Okay, so if you did enjoy it, consider subscribing, and I'll see you soon in the next video. Keep enjoying physics.